Hello. I am going to tell you how to intuitively understand Euler's formula through its derivation. I presume that you understand the concept of Taylor series expansion. If not, please visit the video or the text entitled, "The Simplest Way to Understand the Concept of Taylor Series Expansion" before watching this video. E to the I theta is equal to cosine theta plus I sine theta. Look at this beautiful equation. This is called Euler's formula. It relates the three different mathematical concepts: exponential function, imaginary number, and trigonometric functions. If you substitute theta equals pi, then we get e to the I pi is equal to -1. This one connects exponential function, imaginary number, and pi. The most important point of Euler's formula is that the term e to the I theta plays an important role in science and engineering as the oscillation kernel. Okay. Let's derive Euler's formula by applying the Taylor series expansion at theta equals 0 to e to the I theta. Recall Taylor series expansion at theta equals 0 is f of theta is equal to a0 plus a1 theta plus a2 theta squared plus a3 theta cubed plus etc., where an is equal to 1 over n factorial multiplied by the nth derivative of f at 0. Keep in mind that the derivative of exponential function is exponential function. D over d theta e to the I theta is equal to I multiplied by e to the I theta. Let's calculate the coefficients a0, a1, a2, a3, etc. a0 is equal to e to the I theta equals 0 is equal to e to the I0 is equal to 1. a1 is equal to the derivative of e to the I theta equals 0 is equal to I multiplied by e to the I0 is equal to I. a2 is equal to 1 over 2 multiplied by the derivative of I e to the I theta equals 0 is equal to -1 over 2 multiplied by e to the I0 is equal to -1 over 2. a3 is equal to 1 over 6 multiplied by the derivative of minus e to the I theta equals 0 is equal to -I1 over 6 multiplied by e to the I0 is equal to -I1 over 6. a4 is equal to 1 over 24 multiplied by the derivative of -I to the I theta equals 0 is equal to 1 over 24 multiplied by e to the I0 is equal to 1 over 24. a5 is equal to 1 over 120 multiplied by the derivative of e to the I theta equals 0 is equal to I1 over 120 multiplied by e to the I0 is equal to I1 over 120. And so on. So, the Taylor series expansion of e to the I theta equals 0 is e to the I theta is equal to 1 plus I theta minus 1 over 2 theta squared minus I1 over 6 theta cubed plus 1 over 24 theta to the fourth plus I1 over 120 theta to the fifth plus etc. If this series expansion is split into the even and the odd terms, we get this equation. The even part, which is the real part, is 1 minus 1 over 2 theta squared plus 1 over 24 theta to the fourth etc. The odd part, which is the imaginary part, is theta minus 1 over 6 theta cubed plus 1 over 120 theta to the fifth etc. Well, amazingly, the even or the real part corresponds to the Taylor series expansion of cosine function, and the odd or the imaginary part corresponds to that of sine function. So, we get Euler's formula. E to the I theta is equal to cosine theta plus I sine theta. On the complex plane, theta can be considered as the angle formed by the horizontal axis and the line connecting a point on the unit circle to the origin. If we assume theta evolves with respect to time with a constant speed, we can write theta is equal to omega t, where omega is the speed called angular frequency and t is time. Substituting this into Euler's equation gives e to the I omega t is equal to cosine omega t plus I sine omega t. In this case, the point turns around on the unit circle counterclockwise. This is one aspect of Euler's formula and the reason why it plays an important role as the oscillation kernel. It is known that an actual phenomenon can be obtained by taking the real part of this oscillation kernel e to the I omega t. Why? This will be explained in the video and the text entitled Oscillation Kernel. By taking the real part, we get the oscillation waveform. Next, let's consider what if the variable of the exponential function is not a purely imaginary number but a complex number phi plus I theta. E to the I theta becomes e to the phi plus I theta. This can be written as e to the phi plus I theta is equal to e to the phi multiplied by e to the I theta, and substituting Euler's formula into this equation gives e to the phi plus I theta is equal to e to the phi multiplied by cosine theta plus I sine theta. In most physical and engineering applications, phi and theta are in proportion to time or distance. To understand this equation better, let's consider the case where phi and theta are in proportion to time t. Phi is equal to alpha t. Theta is equal to omega t. Then, we get the time-evolving version of Euler's formula. E to the alpha plus I omega multiplied by t is equal to e to the alpha t multiplied by cosine omega t plus I sine omega t. Depending on the value of alpha, this equation represents different types of oscillation. When alpha equals 0, the e to the alpha t term vanishes. And so this equation is the same as the previous purely imaginary case. In this case, this equation represents a point turns around on the unit circle counterclockwise on the complex plane. By taking the real part, we get the permanent oscillation waveform. When alpha is less than 0, this equation represents a damped oscillation. Starting from the point 1 on the complex plane, the point turns around counterclockwise with an exponentially shrinking radius and converges into the origin, so winding around the origin spirally. If you take the real part of this equation, you get a damped oscillation waveform. This represents the response of most physical and engineering systems which are stable. When alpha is greater than 0, on the other hand, the equation represents a divergent oscillation. Starting from the point 1 on the complex plane, the point turns around counterclockwise with an exponentially growing radius and diverges to infinity. Taking the real part of this equation gives you a divergent oscillation waveform. This represents the response of unstable physical and engineering systems. It is interesting to note that alpha is a criterion which determines whether the system of which response is described by the time-evolving version of Euler's formula is stable or not. So, the oscillation kernel e to the alpha plus I omega multiplied by t represents a permanent, damped, or divergent oscillation. Alpha determines its stability, and omega determines its oscillation frequency. Then, we may write S is equal to alpha plus I omega, and S is called the complex frequency in engineering. Actually, this is the operator of Laplace transform. If you are interested also in Laplace transform, see the video or text entitled, Understanding Laplace Transform in Terms of Complex Frequency. I hope you have reached real understanding of Euler's formula. Thank you.